Some liquids they don't play by the rules. Today, we're going to dive into the really strange science behind fluids, everything from the water in your glass to, you guessed it, that stubborn ketchup in the bottle.
Oh, we have all been there, right? You're standing there, bottle in hand, you turn it over, give it a little shake, nothing. Then you give it that one good smack, and whoosh, out it all comes. It feels like it makes no sense, but believe it or not, there's some seriously cool physics at play here. And today, we're going to figure out exactly what's going on. Okay, so before we can really get into the weird stuff, the rule breakers, we got to know what the rules are in the first place. So let's start with the basics. What even is a fluid? Well, it all comes down to how it deals with a little push and pull. And this is the key difference, right here. Think about it. If you push on a solid, say a brick wall, it might budge a tiny, tiny bit, but then it just stops. It pushes back. But if you push on a fluid, like water, it just keeps on moving. As long as you keep pushing, it keeps flowing. And that right there, that continuous flow, is what makes a fluid, well, a fluid. All right, so in this whole world of fluids, you've got your, let's call them the good guys, the predictable ones. They always do what you expect. We call these Newtonian fluids. Yep, named after that Newton, because they follow his rules to the letter.
And the one big word we need to know here is viscosity. Honestly, it's just a fancy term for a fluid's internal friction. Just think about how thick or syrupy something is. Honey is super resistant to flowing. That's high viscosity. Water, on the other hand, flows super easily. That's low viscosity. Simple as that.
Now here's what makes those Newtonian fluids so predictable. Their viscosity is always the same. It's constant. It doesn't matter if you stir water slowly or whip it into a frenzy. Its thickness doesn't change one bit. So the relationship is super simple. Push harder, it flows faster. That's it.
And you'll see these guys everywhere. I mean, we're talking about water, the air we're breathing right now, gasoline for our cars. Most of the basic fluids we deal with day to day are these predictable Newtonian types. They follow the rules. Okay, now for the fun part. Let's talk about the rebels, the rule breakers. These are the non-Newtonian fluids, and their whole deal is that their viscosity is not constant. Nope. It actually changes based on how much force you throw at them. And this is where we finally get the answer to our ketchup problem.
So these rebels basically split into two groups. First, you have shear thinning fluids. These get thinner or runnier the more you shake them up. Then you've got shear thickening fluids, which do the complete opposite. They get thicker. It's all because of these long chain-like molecules inside them. When you apply force, they either untangle and let things flow, or they bunch up and jam everything.
And ding, 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 here is our answer. Ketchup is a classic shear thinning fluid. When it's just sitting there, it's thick, it's stubborn. But when you give it that good smack, that's the force, you're basically making it less viscous, you're making it runnier, and that's what lets it pour out. It's the same cool trick that paint uses. It spreads easily when you brush it, but the second you stop, it thickens up on the wall so it doesn't drip everywhere.
Then you've got the other side of the coin, shear thickening fluids. The most famous example is that cornstarch and water mix. The stuff you can literally run across. If you hit it hard and fast, it acts like a solid. But the moment you stand still, the pressure drops, it turns back into a liquid, and you start to sink. And yeah, this is the exact same terrifying science behind quicksand. The more you panic and struggle, the thicker it gets around you.
But wait, there's more. For things like ketchup or toothpaste, there's another little wrinkle. They have something called yield stress. It basically means there's a minimum amount of force you need just to get them to start moving. Just tipping the ball over, not going to cut it. A gentle shake? Nope. You need to hit that get moving threshold. You need that solid smack to break the seals, so to speak.
So viscosity is super weird and cool, but it's not the only trick fluids have up their sleeves. There's another invisible force at work, one that lets things seemingly defy gravity, and that's called surface tension.
I mean, it really does look like magic, right? You see an insect, a water strider, just chilling on the surface of a pond like it's solid ground. How does it do that? This has nothing to do with viscosity. This is all about an amazing, powerful film on the very top layer of the water.
Okay, here's how it works. Imagine you're a water molecule in the middle of a glass. You're being pulled on equally from all sides by your buddies. But what if you're a molecule right at the surface? You don't have anyone above you pulling up. So you get pulled down and sideways by the molecules next to you much more strongly. And all that pulling creates this tight kind of elastic skin right on the surface.
And this invisible skin is surprisingly strong. It's strong enough to hold up that little insect for sure. It's also the reason why raindrops pull themselves into almost perfect little spheres as they fall. That's the most efficient shape, the one with the least surface area. It's this incredible force that's just hiding right there in front of us.
So, okay, we've got stubborn ketchup, we've got insects walking on water. This is all really cool, but it's not just a bunch of fun facts. Understanding how all these fluids work, both the predictable ones and the rebels, is actually super important for, well, pretty much everything in our modern world.
I mean, think about it. Engineers use this science to design concrete that flows perfectly but then sets rock solid. Doctors need to understand it because our blood is actually a shear thinning fluid that has to get through tiny capillaries. We use this physics every single day for everything from the lubricants in our car engines to the ink in our printers. And yeah, it even helps us win that epic battle against the ketchup bottle.
So, from now on, when you're painting a wall, or squeezing out some toothpaste, or even just watching the rain, pay a little more attention. Our world is absolutely filled with these weird, wonderful, and stubborn liquids, all playing by their own hidden rules. Now that you know the secrets, what other rebel liquids are you going to spot out there?